Hello everyone, my name is Fred Frispoli and I'm coming to you from Stony Brook University. In this video, we're going to look at examples from Chapter 3 of On's book. In particular, we're going to look at the following discrete probability distributions: the binomial, the hypergeometric, the Poisson, and the geometric distribution. I will cover some frequently asked questions by students. We begin with the binomial distribution. The first thing to notice is that when you have a probability question involving a fixed number of Bernoulli trials, and we'll use n to denote the number. Now these Bernoulli trials are trials that result in two outcomes. We may sometimes call them success or failure. It could be heads or tails, male, female, but these are all examples of Bernoulli trials. So n is the number of trials. P is the probability of a success on each trial. That stays constant from trial to trial. And we use x as our random variable. X is the number of successes in n trials. So we'll use the notation x is binomial with n trials and probability p of success. Some examples would be if a medical treatment is given to n subjects, we could record whether each subject survives. Our random variable x would be the number of survivors among the n subjects. Another possibility, suppose we ask n people, if possible, would you go to outer space? Okay. We could let x be the number of people who answer yes. Another example, among n adults, let x be the number who smoke cigarettes. All right, so to get started, I'm going to show you some questions involving the binomial table. Okay, there are various formulas for the binomial distribution, but the problems we will look at involve the binomial table. Please see the book or the notes for the formulas. They're fairly straightforward. Here we're just going to cover how to use the table because that's sort of an area that needs more coverage. Okay, so suppose x is a binomial random variable. There are 6 trials and p is 0.7. We're going to begin by finding the probability x is less than or equal to 4. And this follow-up question, the probability x is equal to 4. So a binomial distribution table is given in this slide. Right? You'll see this in the textbook near the end. One thing to notice is that these probabilities that are given are cumulative in nature. So up here we have the probability x is less than or equal to some value. And this, by the way, would be the formula that we might use to calculate a certain answer or the values here in the table. So in the question that we were looking at, we knew that n was 6, so we would come down here to this section. P was 0.7, and we were interested in this probability here. Let's just go back. The probability x is less than or equal to 4, so I find my x value here. So I go over to the column with p is 0.7, x is 0.4, and we see the answer is 0.580. So that's how we could get our answer to the first one. I believe I have this given over here. And a 6, p 0.7. Probability x less than or equal to 4 is 0.580. And as I've noted here, This is the red circle on the table. Okay, so I think of this as a cumulative probability because we're actually finding the probability x is 0 plus probability x is 1, x is 2, x is 3, and x is 4. In part B, we want to know the exact probability that x is equal to 4. Okay, so now if we want to do this using the table, we can, but we just have an extra step. The idea is we look at the cumulative probability where x is less than or equal to 4 and subtract off the cumulative probability where x is less than or equal to 3. So here are the numbers. If I go back to this table, you can see over here I'm using this number, 0.580, and subtracting off this number, 0.256, and that gives us the result that we want. The answer is 0.324. So that gives us the exact probability. Okay, then we have another pair of questions, C and D. In part C, x is binomial, where n is 7, and now p is 0.2. So the first question here is find the probability x is less than or equal to 3. And then the second is the probability x is greater than 4. All right, so this question here in part C, this is just another cumulative probability. So we can look that up in the table. We have to go to the section where n is 7, p is 0.2, so it brings us into this column here. And if I want the probability that x is less than or equal to 3, you can see we get 0.967 over here. Okay, again indicated with the blue circle on the table. So we see this right here. Okay, in the next part, we're asking to find the probability x is greater than 4. So to do that, we use the complement, since the table only gives us less than or equal type probabilities or cumulatives. So we convert this using the complement. So this becomes 1 minus the probability x is less than or equal to 3. So we look up the cumulative for 3. That would be this value right here, 0.967. Okay, you can see we have this again. So our answer would be 1 minus 0.967. So let's see, I see that number isn't here, but easy to find. We get, what do we get? 0.033, I believe. Okay, so there's a problem using binomial probabilities and the table. Okay. Here's a second binomial distribution example. So this one has a little bit more context. Suppose we know that the probability is 0.1 that a certain device fails a comprehensive safety test. So another way of saying it is there's a 10% chance a device fails a safety test. What are the probabilities that among 5 of these devices, A, at most 2 will fail, and then B, at least 2 will fail? So I have at most 2 will fail, so we want to sort of think along the lines, I need to find the probability when x is 0, x is 1, and x is 2. So the table gives us cumulative probabilities, and now we have to look at the section where n is 5 and p is 1. So let's take a look at that. If we go back over here, I think I have another table, yes. So here's the section where n is 5. We know p is 0.1, so the probability at most 2 will fail will be given right here with this value, 0.991. right? So here again, you could see the red circle, 0.991. The probability x is less than or equal to 2. In part B, we have a question where we want to find the probability at least 2 fail. Okay. Now, if you're careless, you might think that one is the complement of the other, but that's not quite the case. Okay. The probability x is greater than or equal to 2 is equal to 1 minus the probability x is less than or equal to 1. Right? This would include the cases where x is 2, 3, 4, or 5. Okay. But we want to solve that using the complement. So 1 minus the probability x is either 0 or 1. So again, we could go back to the table, and now it's also in the red circle. We need to look up the case where x is 1. Okay, so that would be right here. So I have 0.919. So we're looking at 1 minus 0.919. Okay, and you can see we get a final answer of 0.081. Okay, so a couple other facts about the binomial distribution. It's surprisingly easy to find the mean of a binomial random variable. If x is binomial with n events, okay, or n trials, and probability p of a success, then the expected value, which we'll denote by either e of x or mu, is equal to n times p. Okay. Also, the variance has a nice, easy formula to use. If I want the variance, it's n times p times 1 minus p. So, for example, suppose we're asked to find the mean and variance of the probability distribution for the number of heads obtained in 10 flips of a balanced coin. So, we know that 10 is binomial, x is binomial, the number of trials is 10, and p is 0.5. So we get our mean, n times p, is 10 times 0.5, which is 5. And our variance is n times p times 1 minus p. So we get 10 times 0.5 times 0.5 again. We get 2.5. So we have these nice, easy formulas for the binomial distribution. And these are worth really memorizing because they will come up later on in the course, really repeatedly through the course. Okay, so here's an exercise. I suggest that you read through this and stop the video and try to solve this. So the problem is that suppose we know David did not study for his psychology exam consisting of 15 true or false questions. He used the technique I called wild guessing on each question. Now suppose he needs to score 10 or more correct to pass. What's the probability that he will fail the exam? And part B, find the probability that he answers either 6, 7, 8, 9, 10, or 11 questions correctly. So use a binomial table with n is 15. You could find that in the book. If you can't find that in the book, most of these tables we look at can be found by running a Google search. Simply search binomial table. You'll see one that comes up. Just be careful. The binomial table we were looking at before is what I would call a cumulative binomial table. But some of these tables give you exact values. So make sure you understand what you have. So if you stop the video here, try to work this out. So solutions are given here. X is binomial, n is 15, p is 0.5. So the probability he fails is the probability x is less than 10. This should work out to 0.8491. So I'd say about an 85% chance that this is a failing strategy. In part B, you're asked to find the probability x is between 6 and 11, inclusive. So again, this is the probability. X is either 6, 7, 8, 9, 10, or 11. So if we have a cumulative distribution table, we could find the probability x is less than or equal to 11. Okay, make sure you use n is 15, p is 0.5. So we get 0.9824. And then subtract from this the probability x is less than or equal to 5. So subtract off 0.1509, and we should get right around here, you see 0.8315. Okay, so that's our first discrete distribution. Now, the second distribution we'll look at is called the hypergeometric distribution. So it's a little bit like the binomial, only here we're sort of assuming no replacement. So we have a finite population with n individuals, and we're sampling without replacement. We could think in terms of outcomes are either a success or a failure. And let's say that there are A successes in the population. Our sample size will still be n, and we assume each subset of size n is equally likely to be chosen. So the probability, our random variable, capital X is equal to x, is given by A choose x times n minus A choose n minus x divided by the number of subsets of size lowercase n. So this is n choose n. Okay, so it may actually be easier than it first appears. In fact, many of these hypergeometric distribution problems can be given just from reasoning what you know using counting formulas. Okay, so suppose we have a situation where in a box of 25 external hard disks, there are 2 defectives. Now, an inspector examines 5 of these. We want to find the probability that there's at least 1 defective hard disk amongst the 5. So we define our random variable. Let x be the number of defective hard disks. Right? So what values can x take on here? At least capital X can take on anywhere from 0 to 5. However, let me take that back. There's only 2 defectives. Okay, so even though we're going to examine 5, there's only 2 defectives. So x could take on the value 0, 1, or 2. All right, so we let x be the number of defective hard disks. Then x has a hypergeometric distribution. And we could think of this as the probability, our random variable x is equal to some value x is 2 choose x. So this is the number of ways to choose the defectives. And then 23 choose 5 minus x. So this is the number of ways to choose the non-defectives. Divided by 25 choose 5. That's the number of ways to choose 5, to choose our subsets of size 5. Okay, so we can work this out. Okay, now we want the probability x is greater than or equal to 1. Okay, so we're looking at 1. minus the probability, x is equal to 0. We could figure out the probability x is equal to 0 using this formula up here with x equals 0. So you could see we could work this out. We get 1 minus this expression. If we sort of expand this out using factorials, cancel out like terms, this works out to be 1 minus 0.633. So that gives us here 0.367. Okay. Our next distribution is the Poisson distribution. Okay. So what makes a distribution of Poisson? Well, when the probability that an event occurs in the interval is proportional to the length of the interval. That's one condition. The second condition is that two events cannot occur at exactly the same instant. And the third is that the events occur independently. When these conditions are satisfied, the probability of x events occurring in a time period t is called a Poisson random variable with parameter lambda. And we have a nice formula to calculate these probabilities. Our formula looks like this. The probability, our random variable x is equal to x, is given by lambda to the x times e to the minus lambda divided by x factorial. And this parameter lambda we can think of as the average rate of occurrence. Okay, so you can see this formula. We have E is equal to the well-known 2.71828. The variance here, surprisingly, is also equal to lambda. So I have an average value of lambda, and we have a variance of lambda. So this is a fairly easy formula to use. It's useful in certain cases, especially when you have an exact probability. Some examples of when to use a Poisson distribution. If you're trying to calculate the number of occurrences over a given time period or a given area. An example might be the distribution of hurricanes in Florida during a certain year. Another one might be the number of arrivals at a toll booth over a certain period of time. It could be the number of arrivals in a minute or the number of arrivals in an hour. And could also use the Poisson to study the number of hits a website gets, let's say, in 1 minute. So there's also a cumulative table given here. I'll show you what it looks like here. Here you could see this is a table that can be used for certain values of lambda. Right, so we could start with 0.1, 0.2, and this goes up to 1.8 here. In the next section, it goes from lambda equals 2 to 5.5. So if you have a value of lambda here, we could use this. This is nice. It gives us, again, the cumulative probabilities. But if you have a value of lambda that's not here, then we have to use the formula. So here's an example. Suppose the number of hits on a certain website follows a Poisson distribution with a mean rate of 4 hits per minute. So we ask, what's the probability that at most 5 hits are received in a minute? Okay. Part B looks almost the same, but here we're asking what's the probability that exactly 5 hits are received in 15 minutes. So again, I see this should just be 1 minute. All right, so let's go through this solution. So we want to know the probability at most 5 hits are received in a minute. And we know that lambda is equal to 4. The website receives 4 hits per minute. So our random variable x is Poisson, with lambda equals 4. The question we're asking is what's the probability at most 5 hits are received. So our x value is 5. We're interested in the probability x is less than or equal to 5. So we can look this up in the table. So here I've shown you the table over here. We find the value of lambda. Okay, so here's the value of lambda. We do that first, and then we find our x value is 5. So our answer here would be 0.7851. So that's how we get at this number. Now for part B, let's say we want to know the probability of exactly 5 hits. This is in 1 minute, right? Not 15. Exactly 5 hits in 1 minute. Then we could get this answer 2 different ways. Here we could use the formula. The probability x is 5 is e to the minus 4 times 4 to the 5th over 5 factorial. So I get 0.1563. So we get that directly, very quickly. So we could solve this problem using the table, but now we have to remember the table gives you cumulative values. So we break this up to find the probability x is equal to 5. We look at the probability x is less than or equal to 5 minus the probability x is less than or equal to 4. We look up these values in the table. Let's take a look at the table again. So here you could see this. This is the value you get where x is 5. This is what we get when x is 4. And now we would have to subtract these two values to get the exact probability. Okay, so we get 0.1563, same as what we had before. Okay, let's take a look at another example, also based on hits that a certain website receives, but here we have an extra step. So suppose we know the number of hits of a certain website follows a Poisson distribution with a mean rate of 4 per minute, just like in the previous example. But now we want to know what's the probability there's at least 63 hits received in 15 minutes. So now we're changing the time period. Okay. So in this problem, we need to adjust lambda. Since the average rate of hits is 4 hits per minute, in 15 minutes, the average rate will be 60 hits over a 15-minute period. So our lambda that we need to use in any formula must be equal to 60. So to calculate the probability x is greater than or equal to 63, we first see we have a greater than or equal to probability, so we could solve that using the complement. So this is 1 minus the probability x is less than or equal to 62. So this would be 1 minus e to the minus 62 times 60, that's our lambda, to the 62 over 62 factorial, right? That's our x factorial term. So we could work this out. It does turn out to be a manageable number. This whole piece over here, or this probability, simplifies to 0.0066. When we subtract, we get 1 minus 0.0066. So we end up with a final answer of 0.9934. Okay, for our last discrete distribution model, we're going to consider the geometric distribution. So here, once again, each trial can result in either success or failure. The trials are independent. The probability of a success is P, but now the idea is we continue until the first success occurs. So this probability distribution function is simply P times 1 minus P to the x minus 1. And here we have an E of x. Expected value of x is 1 over P. All right, so as an example, suppose we know that a horse has a probability of winning a race 30% of the time. That's pretty good. What's the probability that on a certain day the horse wins his first race on the third race? Okay, so just to be clear here, we want to know the probability that he loses the first, loses the second, and then wins the third. So that's where he's winning his first race. Well, that's fairly easy to calculate. You really don't even need the formulas that I just showed you. So we get 0.7 squared, right? That's the probability he loses the first two races. And then a 0.3 because he's winning on the third race. So we can multiply these because these are independent probabilities. We get a final answer of 0.147. If we have a similar question, but we ask what's the probability the horse wins his first race on the fifth race, well, then we know he would have lost the first four and then won a race. So now the calculation looks like 0.7 to the fourth times 0.3, and this works out to be 0.07203. Okay, so we've reached the end of this video. There's also another video on chapter 3 called Chebyshev's theorem. So thank you for watching.